of electromagnetic wave, let us consider an example. So a transmission line which is having a characteristic impedance of Z0 and which is fed to the load through a generator. Okay, so the generator is having a fed to the transmission line and transmission line is fed to the load. So in this way, so whenever the wave is passing, electromagnetic wave is passing through a transmission line, so if the transmission line is having a characteristic impedance, so which is nothing but Z0, and the load is having some impedance value which is nothing but a ZL. So these two are equal when the wave is getting terminated. If these two are mismatched, so that means ZL and Z0 characteristic impedance are mismatched, then the wave is getting reflected. Okay, so this can be seen through a diagram. See this diagram. So this is an example. This is a generator. Okay, and this is a generator. So which is having a transmission line. So the transmission line is fed to load. Okay. So the transmission line is having a characteristic impedance Z0 and the load is having a characteristic impedance of ZL. So when the electromagnetic wave is traveling, so when it reaches to the load, so again it is getting reflected. So when this happens means ZL is not equal to Z0. If ZL is equal to Z0, the electromagnetic wave is terminated through the load. Okay. So if there is a mismatch between ZL and Z0, then the wave is getting reflected. So at that time that is called as a standing wave. The standing waves are said to be produced along the line. In that case, the standing waves are produced along the line. Okay. Standing wave is nothing but incident wave and a reflected wave. There is no transmitted wave. Okay. Consider a uniform plane wave which is traveling with equity on two mediums, from medium 1 and medium 2. The wave is to be traveled from medium 1 to medium 2. So what happens is these two mediums having two different intrinsic impedances. So the part of the wave is incidented at the boundary. So what happens is when the wave is incident to the boundary and the wave, some part of the wave is back to the reflected back. Okay. Some part of the wave is reflected back to the medium 1 and some part of the wave is transmitted in medium 2. So in this way, depending upon the manner in which the reflection, the incident wave is incidented to the boundary, so there are two cases of incidences. One is a normal incidence and one is the second one is the oblique incidence. So let us consider these two incidences between two dielectrics and a plane conductor and a dielectric. Okay, now we'll see about a normal incidence and a oblique incidence. So what is about a normal incidence? When a uniform plane wave incidences normally to the boundary between a two mediums, so this is known as a normal incidence. So this can be explained through a diagram. So this is a boundary. So the wave which is traveling in a normal direction, okay, is traveling in a normal direction to the boundary and it touches to the incident to the boundary. So this is called as a point of incidence. So what happens here? The uniform plane wave incidence is normal to the boundary between a two mediums. Suppose, so I am considering a two different mediums. So this is one of the examples. Okay. Now I will see about two different mediums. So this is a medium 1 and this is medium 2. So the wave which is traveling in a medium 1 and touches the boundary normally. Okay. And some part of the wave is reflected back. And some part of the wave is transmitted to medium 2. So here what is meant by normal incidence means when the uniform plane wave incidence normal to the boundary between two mediums, then it is called as a normal incidence. Now what is about an oblique incidence? Let us consider this. When a uniform plane wave or incidence obliquely to the boundary between the two mediums. So let us consider, okay. So this is the boundary between two mediums. So this is medium 1 and this is medium 2. Okay. So when the wave in a medium 1 is obliquely to the normal to the boundary between two mediums, so that means to the surface it is making some angle. Okay. So that is nothing but an oblique. So whenever the uniform plane wave incidence, so this is an incidence, okay, so and it is reflected back and is again reflected back to the medium 1 or medium 2. So whatever, it is considered as the latter. Okay. So what you mean by oblique incidence means when a uniform plane wave incidence obliquely, it is making an angle to the boundary between the two mediums, then it is called as an oblique incidence. Okay. Okay, now we'll see about a normal incidence between two dielectric mediums. Okay, so let us consider x, y and z axis. So you can see from this diagram here, so x axis and z axis. Where is the y axis? There is no y axis here. So this dot line is represented as a y. So why it is represented as a dot as a y means, so let us consider Fleming's right hand rule. So here z is a forefinger, x is a forefinger and z is a thumb and y is pointing outside of the taper, so it is nothing but a middle finger. Okay. Now according to right hand thumb rule, thumb denotes the outward, so outward current is always represented as a dot. So in this way, so we consider that y as a outward of the, why? Because if the axis is coming out of the taper, so the y axis is treated as a dot here. Okay. Now this normal incidence at the plane between a dielectric boundary, that means we are considering here medium 1 and medium 2 are both are dielectrics which are having a different medium. So epsilon 1 is a medium 1 and epsilon 2 is a medium 2 of the dielectrics. Okay, it is having a permeability and conductivity and a intrinsic impedance, which is having a different permeability, different conductivity and different intrinsic impedance. So there are nomenclature. Okay, let us see. E suffix I is the electric field intensity of the incident wave, and Hi is the magnetic field intensity of the incident wave, and Er is the electric field intensity of the reflected wave, and Hr is the magnetic field intensity of the reflected wave. So I already told that. So what do you mean by normal incidence? So when the wave is traveling and it hits the boundary perpendicularly or normal to the boundary, so what happens? Some part of the wave is fed back to the medium 1 and part of the wave is transmitted in medium 2. Okay. So here Ei is the electric field intensity of the incident wave and Er is the electric field intensity of the reflected wave. In the same way, these are the nomenclature where E1 and E2 are the total intensities of the medium 1 and E2 is the in total electric field intensity of medium 2. Similarly, H1 and H2 are those. Okay. Now we'll see about a normal incidence at the plane between a dielectric boundary. So this is the boundary. So this x-axis is treated as a boundary. Okay. Now I am considering the electromagnetic waves. So you know that the if the incidence wave of electric field intensity is in x direction. So this is the incident wave electric field intensity. Okay. Now the H field must be in normal to this direction. So this is represented as z. Okay, h suffix I. Okay. So now the propagation, direction of propagation of the wave must be curl of these two. Okay, in this direction. So this is the direction of propagation of this particular wave, incident wave. Okay. So this is you can write this is the incident wave. Okay. Now what about when it touches the boundary? So what happens? It again reflected back. Some part of the wave is reflected back. And this is ER and this is HR. So this is the reflected wave. So we can write here is the reflected wave. Okay. Now what is the transmitted wave? So we can write in the transmitted wave as the same direction as that of a incident wave. Incident wave. So this can be represented with ET. ET is the electric field intensity of the transmitted wave. So the transmitted one must be in a medium 2. Okay. So what is represented? It is a HT. It is reflected. Sorry, this is transmitted wave. This can be represented as a transmitted wave. Okay. Okay. Now by seeing this diagram, we can say that the wave which is traveling in this particular direction, okay, when it hits the boundary, so whatever, some part of the wave is reflected back and some part of the wave is transmitted to the medium 2. Okay. Now what happens? So from this we want to derive a particular derivation. Okay. For this, what is the reflected? I want a reflected coefficient. So it can be treated as a gamma. So in order to derive the gamma, we need to consider some of the equations. Okay. In order to derive the reflection coefficient, we need to consider some of the equations. So let us see. So we can write the equations as, so in this medium 1, so E1 is nothing but a total electric field intensity of the medium 1. So here the total electric field intensity is nothing but a incident wave electric field intensity and reflected wave electric field intensity. This can be seen from this diagram. So we can write E1 vector as EI vector plus ER vector. Okay. Now in the same manner I can represent H1 vector, magnetic field intensity. Hi is a incidence and HR is a reflected. So in the same manner we can represent E2. E2 is a electric field intensity, total electric field intensity in medium 2. Okay. So in medium 2 is nothing but a transmitted wave only. So the electric field intensity is for transmitted wave. In a similar manner, H2 can be written as HT is nothing but a transmitted wave of a magnetic field intensity. Okay. So now I want to consider boundary conditions. So when the incident wave strikes the boundary, so according to the boundary conditions, so at boundary Z is equals to 0, impedance is 0. So the tangential components are equal according to the boundary. Tangential components are equal. So the E and H are transverse in nature, so that the E and H are tangential to the boundary. Okay. So from this, the total electric field intensity of the medium 1, which is equals to total electric field intensity in medium 2. Okay. So what I am writing is, so according to the boundary conditions, at the boundary, so tangential components are equal. So here at the boundary, the tangential components are nothing but a electric field intensity of the incident wave and the electric field intensity of the reflected wave. In the same manner, we can write E as E tangential to the boundary, so E1 is equal to E2. So E1 can be written as EI plus ER. E2 can be written as ET. Okay. Similarly, H1 is equal to H2. This is H1 is equal to H2. So we can write HI plus HR is equal to HT. Okay. So this is the equation 1 and this is the equation 2. So why I am writing like this means, at the boundary the E1 and E2 are equal. So here E1 is nothing but a electric field intensity of incidence and reflected wave, and the E2 in the medium 2 electric field intensity of the transmitted wave. In the similar way, E and H tangential components are at the boundary are equal. So H components are also equal, medium 1 and medium 2. So medium 1 is nothing but similar to the E as I am representing as a H. Okay. So from these two equations, so we can write it. So I am rewriting the second equation in terms of a first equation. So I am converting the second equation. Converting second equation in terms of E. Okay, how I convert it in terms of E means, so by using the relation EI is equal to intrinsic impedance of the medium 1 of HI, and ER is equal to minus, why the ER is a opposite to that of incidence wave, so I can represent this negative sign of medium intrinsic impedance medium 1 and HR. Okay. So by using this relation, so we can write HI is equal to EI by intrinsic impedance 1. Similarly, HR is equal to ER by intrinsic impedance 1. Okay. So this is a negative. Okay, this is negative. Why? Because here we are having a negative sign. So we'll see about converting the second equation in terms of E. So HI can be written as EI by eta 1. So put this in this HI expression. So you'll get EI by eta 1. So HR means ER by eta 2, eta 1. ER by eta 1. So which is equal to HT. HT can be written as ET by, so this is transmitted which belongs to medium 2. So can be represented as eta 2. Okay. Now we'll see, taking the common of E1 and eta 1. So we can write EI minus ER. So it is equal to ET by eta 2. So EI minus ER is equal to eta 1 by eta 2 ET. Okay. So this is our third equation. And this is how we can see first these two are first two equations, and this is the third equation. So as 1 and 3 equations. Okay, so 2ei, so you get by adding to these two equations you will get 1 plus eta 1 to eta 2 et. Okay, so 2ei is equal to eta 2 plus eta 1 by eta 2 bracket of et. Okay, so now ei is equal to eta 2 plus eta 1 by 2 eta 2 eta 2 et. Okay, now transmission coefficient can be represented as tau, which is equal to et by ei. So transmitted wave to reflected wave, so it is equal to, so this is a bracket, so the ratio of transmitted wave electrical intensity to incident wave electrical intensity is nothing but a transmission coefficient. So this value is, we can write 2 eta 2 by eta 2 plus eta 1. So this is the equation for transmission coefficient. But we want to derive the gamma, which is nothing but a reflection coefficient. Okay, so now by taking this is the equation, we can write this is the equation 4. Okay, equation, and by taking et, we can write et in terms of et can be written as ei minus er. So by using a third equation, so et can be written as, now et is equal to eta 2 by eta 1 multiplied of ei minus er. Now replace this et value in the place of this et in the first equation. So I am writing now ei plus er is equal to, this et can be written as eta 2 by eta 1 multiplied with ei minus er. Okay, now multiply on both sides, so ei plus er is equal to eta 2 ei minus er. Okay, so multiply on both sides, ei er eta 2 ei 1 minus eta 2 er. So now take ei common on both sides, so you will get eta 1 minus eta 2 is equal to minus eta 1 er minus eta 2 er. So okay, now we can see from this incident wave and eta 1 eta 2, so take here minus er, so eta 1 plus eta 2 here. Okay, so this minus symbol is, so now I want a reflected wave to incident wave, so this is nothing but a gamma reflection coefficient, which is nothing but a reflection coefficient. So that it is the ratio of electrical intensity of reflected wave to electrical intensity of incident wave. So now we can write eta, so this minus symbol is same here, so we can write it as a eta 2 minus eta 1 by eta 2 plus eta 1. So this is the reflection coefficient which is derived for how. So by using these two equations, transmission coefficient equation and reflection coefficient equation, so we can say 1 1 plus gamma is equal to tau. Okay, so by using these two equations we can say 1 plus gamma is equal to tau. Okay, so this is another equation. So now we can say that this is the fifth equation and this is the sixth equation. Now we can say that this gamma value will lie in between 1. Okay, so this is a normal incidence plane between a dielectric boundary. Okay, so we have derived the transmission coefficient equation and a reflection coefficient equation between a two boundary between a two dielectric mediums. Okay,